All right, let's dive into the science of strategy. We're going to unpack one of the most powerful ideas out there for figuring out how to make the right choice, especially when your best move depends completely on what someone else decides to do.
I mean, just think about it for a second. Whether you're in a business deal, a political standoff, or even just figuring out where to meet up with a friend, your best move is almost never made in a total vacuum, right? It's always a reaction to what you expect the other person to do. So, how in the world do you find a stable, predictable outcome in this crazy web of decisions?
You know, for a long time, people had tried to predict the outcomes of these kinds of games. But they found out pretty quick that just trying to outguess your opponent, getting stuck in that endless loop of, well, he thinks that I think that he's going to think, it just wasn't reliable enough.
One of the first tools people came up with tried to solve these games by just, logically crossing off all the obviously bad choices. And yeah, sometimes that works like a charm. It leaves you with one clear answer. But a lot of the time, it only gets you part of the way there. Or worse, it doesn't help at all. It just can't quite get a grip on the problem. So what we really need is a concept with, as our source material perfectly puts it, more bite. We need a sharper tool, something that can give us a much more precise and reliable prediction. And that very tool, developed by the incredible John Nash, is built on one beautifully simple, powerful idea. And that idea is called the best response. Seriously, before we can even begin to understand the equilibrium, we have to get our heads around this foundational concept first.
A best response is, well, it's pretty much exactly what it sounds like. It's the single best move you can possibly make, given a specific move by your opponent. If you knew, for a fact, what they were about to do, what would you do to get the absolute best outcome for yourself? That right there, that's your best response.
And finding a best response in one of these game charts or a matrix is actually a really simple process. First, you just assume your opponent makes a specific move. Let's say they pick the first column. You can literally take your hand and cover up the other columns. Now, just looking at that one column, you find your highest possible number, your biggest payoff, and you underline it. Then you just do it again for every other choice they could make. It's really that simple.
And once we know how to find everybody's best responses, well, that's when we can unlock the real magic of the Nash equilibrium. So, a Nash equilibrium is the state of perfect stability. It's an outcome where every single player in the game is making their own best response to what all the other players are doing. Think of it as a point of mutual best response. I'm doing the best I can, given your move, and you're doing the best you can, given mine.
And this is the core of the idea. It's just brilliant. Once you land in a Nash equilibrium, nobody has any reason to change their mind on their own. Why? Because if they did, their payoff would either go down or at best stay the same. Everyone is locked in because they're already doing the best they possibly can. No regrets.
Okay, this all sounds great in theory, but what does it actually look like? Let's check out how this whole concept plays out in 4 of the most famous games in all of game theory. First up, the all-time classic, The Prisoner's Dilemma. The setup is really simple. 2 partners in crime get arrested, and they're held in separate rooms. They absolutely cannot talk to each other, and the police offer each of them the exact same deal. Let's break down what we're looking at here. The numbers are years in prison. So remember, lower is better. If they both stay silent, they each get just 1 year, okay? If one confesses and the other stays silent, the confessor walks free, gets 0 years, while the other poor guy gets 10 years. And if they both confess, they each get 5 years.
So let's find the best responses. If player 2 confesses, what's player 1's best move? Well, it's to confess too. 5 years is way better than 10. Now, what if player 2 stays silent? Well, player 1's best response is still to confess. Going free is better than a year in jail. And the exact same logic applies to player 2. So the only spot on this board where both numbers are underlined, the only mutual best response is for both of them to confess.
And here's the really powerful and honestly kind of tragic lesson of the prisoner's dilemma. By each of them just pursuing their own individual best interest, they end up in a situation that is collectively worse for both of them. They both get 5 years when they could have cooperated and both gotten only 1. This exact tension is at the heart of everything from price wars between companies to international politics.
Okay, let's look at a totally different kind of problem. In this classic game called the Battle of the Sexes, Anna and Felix really want to hang out together, but they can't get in touch to coordinate. The problem is, Felix would rather go to the football game, and Anna would much rather go to the opera.
So looking at this matrix, you can really see their dilemma. They get a pretty good payoff if they just end up at the same event, but their absolute best payoff comes from being together at their personal favorite event. The worst possible outcome for both of them is ending up alone. This is all about coordination.
Now, when we apply our best response method here, something really interesting happens. If Anna goes to the opera, Felix's best response is to join her. And if Felix is at the opera, Anna's best response is to be there too. So boom, that's one equilibrium. But the exact same thing is true for the football game. This gives us two stable outcomes, two Nash equilibria, even though each of them prefers a different one.
Okay, our next game really raises the stakes. This is a pure coordination game, and it's illustrated perfectly by the classic bank run. Two depositors hear a nasty rumor that their bank might be in trouble. They each have to decide, do I withdraw my money now or do I wait?
Check out the payoffs. If depositor 2 withdraws, depositor 1's best response is to withdraw too, right? If everyone else is panicking, you better panic with them. But if depositor 2 waits, depositor 1's best response is also to wait and get the full payout. So again, we have two Nash equilibria, a really bad one where everyone withdraws and the bank collapses, and a good one where everyone waits. It's a total self-fulfilling prophecy, and it's all driven by what you expect others to do.
And finally, let's look at an anti-coordination game, the legendary game of chicken. You've seen this in the movies. Two cars drive straight at each other. The first one to swerve is the chicken.
The payoffs here are, well, they're intense. The absolute worst outcome for everybody is a crash if nobody swerves. The best is being the one who bravely stays straight while the other person chickens out. So if player 2 swerves, your best response is to stay straight. But if player 2 stays straight, your best response is to swerve. So the only stable outcomes, the Nash equilibria, are when one player swerves and the other stays. You want to do the exact opposite of your opponent.
So, from prisoners and couples to bank depositors and daredevils, we see this powerful pattern emerge again and again. The Nash equilibrium shows us that stability can pop up in some surprising and, yeah, sometimes not so great ways. It reveals how rational individual choices don't always lead to the best result for the group. And this logic is a fundamental tool for understanding everything from corporate price wars to how animals compete for food in the wild.
So the next time you see two gas stations across the street from each other with the exact same price, or you wonder why political campaigns seem to get stuck in these nasty negative ad loops, think about mutual best responses. This framework, this way of seeing things, it's absolutely everywhere. The only question is, where do you see it?